Hi guys, and welcome to another in the series of preliminary chemistry videos, this one in the topic of metals. And we're going to look at the activity series of metals today in metals video number 5. So what we need to do then is we need to first of all realize that different metals have different reactivities, and we've kind of linked that idea to the idea of how easily we find them in the Earth's crust. Some of them are found uncombined, some of them are combined as compounds, but are reasonably low in their activity, and therefore they're easier to extract. And then some of them are very reactive and combine to form very stable compounds that are much or require a lot more energy in order for us to purify the metal. But the other thing that we can do is we can look at reactions of the different types of metals in similar reactants, that is, in dilute acid, in cold or warm water, or in oxygen, to excuse me, to allow us to build up a series of metals based on their reactivity. And in fact, this is what the activity series of metals is all about. It's basically just an order of metals from least reactive to most reactive. So here's a couple of them. Potassium is one of the metals that we would put near the top of our activity series. It's a group 1 metal, and it's very reactive. Okay, it's one of the alkali metals, and it's very reactive. Just underneath potassium would be sodium, which is also a group 1 metal. Then barium and calcium and magnesium are all group 2 metals. And it's not until we get down to zinc that we start looking at transition metals. And these ones down here are pretty much all transition metals from here in. Copper is one of the more stable, so this is a more stable, low activity metal. And of course, I've left off this little chart things like gold and silver and platinum, which are also very stable and reasonably inert. So after magnesium here would come, after aluminium here would come magnesium. So if I had it slightly longer, we could put more metals into this. And in fact, you will find a table in your textbook which shows a much larger number of metals than the ones that I've included here in terms of an activity series. The other thing that's important to be aware of is the fact that we will provide you with not only a periodic table, but a table of standard reduction potentials. The standard reduction potentials show you how readily most ions, metal ions, will pick up an electron and form their metallic element. I guess vice versa, that information also provides you with how easily it happens in reverse. That is, how easily a metal will lose one or more electrons in order to form its most common ion. Either way, we can do this theoretically by looking it up in a book, or we can do it experimentally by actually carrying out a series of experiments in order to compare the reactivity of different metals. So in general then, the more reactive a metal is, the more readily electron transfer occurs. And really what we're talking about when we're talking about reactivity is we're talking about electron transfer. So most of the time, the most common reaction we're looking for is a metal becoming a metal ion, say a 2+ ion, and releasing 2 electrons. Now of course metals can't do this in isolation. The electrons have to go somewhere. So usually this is going to occur in some sort of a situation where another species is going to be taking in these electrons and is going to be including them as part of their own structure. This is the kind of reaction we get when, for example, magnesium reacts with dilute hydrochloric acid. What happens is that the magnesium transfers its electrons to the hydrogen ions that are in the acid. The hydrogen ions take in those electrons, reform hydrogen atoms, and then link together through a covalent bond to form hydrogen gas. The magnesium has become an ion, so magnesium 2+ ions, and it has gone into the solution. We can show these processes using what we call half equations. This shows which species is gaining electrons and which species is losing electrons. When we put these two together, we get an overall equation, or a net ionic equation, made up from the two half equations. And the two half equations are going to be an oxidation, which is a loss of electrons, and a reduction, which is a gain of electrons. And hopefully, you will, when you're putting these two half equations together, you'll do them in such a way as to cancel out the electrons, so that we've not created or lost any electrons, but that those electrons are being transferred from one species to another. So here is an example of that. So for the previous slide, we looked at what happens when magnesium is placed into a solution of acid, dilute acid, is that the magnesium solid will displace the hydrogen ions from the solution. That is, they'll actually push them out. The hydrogen ions will take in electrons and form hydrogen gas, and this gaining of electrons is called reduction. Reduction is gain. While the magnesium is losing electrons, and because it's losing electrons, it's called oxidation. Together, they're called a redox couple, where one species is gaining electrons and the other is losing them. When we put these equations together, we find the magnesium and the hydrogen ions on the left side, or on the reactant side, and the magnesium ion and the hydrogen gas on the product side. Notice that we have two electrons on either side of our arrow, and so as a consequence they will cancel out. But notice something else. If we were to do this with, say, for example, hydrochloric acid, then we would have chloride ions also in the solution. But what would be happening with the chloride ions is that they would be present before the reaction occurred as a result of the ionization of the hydrochloric acid, but they're also in the solution after. They don't precipitate out. Magnesium chloride doesn't form a precipitate, so the chloride ions will stay. So we call these spectator ions. And because they are spectator ions, nothing happens to them. They're neither oxidized nor reduced, and they just remain in the solution all the way along. So we can actually cancel them out of our reactions. We don't need to consider spectator ions if there has been no change in what's actually happened to them in terms of oxidation or reduction. And that's why the chloride ions don't actually appear in any of these half equations. So, could you write an equation to represent the reaction between aluminium and sulfuric acid? Well, we probably need a little bit more information now about what sort of equation we can write, because we can write a general equation. Aluminium is a metal, so aluminium, solid, combines with sulfuric acid, which is an aqueous solution, and it's going to form aluminium sulfate, which is a salt, and hydrogen gas. And the aluminium sulfate will be in aqueous solution, probably. The hydrogen gas will be given off as a result of this particular reaction, and I've created aluminium sulfate as a species by regarding the sulfate as having a 2- charge and the aluminium as having a +3. And again, check your periodic table for aluminium. Sulfate is one of these polyatomic ions we just have to know, unfortunately. And so I've done the cross method, put the 2 there and moved the 3 across, and I've got to have 3 lots of everything. Now my problem is that I don't have a balanced equation here. And the main reason I don't have a balanced equation here is that I have 3 lots of the sulfate group. And the sulfate group's here and it's kind of hung together. So if I put 3 in front of the sulfuric acid, then I will have my 3 covered. Of course, I now have 6 hydrogens over here, so I'll need a 3 in front of this. And I have 2 aluminiums here, so I'll need a 2 in front of here. So now my equation is balanced. But it may well be that I want to find a net ionic equation for this process as well, to try and understand what's actually going on. So what's actually going on is an aluminium solid has become aluminium ions and has released 3 electrons. So therefore, it's been oxidized. The hydrogen ions, the H+, have gained an electron in order to become H2 gas. So it has been reduced. Now, if I wanted to cancel each of these out, then what I would need to do is to have these 3 electrons here balanced by 3 electrons here. My problem is going to be that if I have 3 electrons here, then I'm going to have a 3 out the front of the hydrogen. But I have an even number on the right side of that equation, and then there would be an odd number there, and I don't like to have halves. So what I'm going to do is I'm going to get my little orange color, and I'm just going to double that, and double that, and double that. And then with my yellow color, I'm going to bring those 6 here into here, 6 there, which makes 6 of them, and 3 of those. So what you can see is that when I then put them all together in order to make an overall balanced equation, my 2 lots of electrons, 2 lots of 6 electrons are going to cancel out, and I'm going to end up as my net ionic equation 2Al solid plus 6H plus gives me 2Al3 plus 3H2 gas. Notice that when you're working through these sorts of examples, the 6H pluses have actually come from the acid, and because the formula for the sulfuric acid is an H2, 3 2s are 6, so I am going to have 6 hydrogen ions in total on that side of the reaction. And also notice that the 6 pluses here means we have a 6 plus charge on the left side, or the reactant side of our reaction, and I have 2 3s, 6 plus on the right side of my reaction. So it's not just important with these sorts of equations that you balance the atoms on either side, you must also balance the charge. So this is my net, oops, go back to white, my net ionic equation. Thanks for watching.